Okay, this video we are going to start looking at titration curves. You looked a little bit at titration curves last year in Chem 20, kind of introduced it to you. We showed you what it looked like for a strong acid with a strong base where both of them were monoprotic. Okay, so we're still going to look at those this year, but we're also going to add in some weak stuff and we're going to add in some polyprotic as well. Okay, so yesterday we talked about endpoint versus equivalence point. Those are still some important terms you want to make sure you're familiar with. But what you're going to find is generally when we are doing pH curves, I don't want to say we don't use an indicator, but we don't use an indicator to tell us when to end the titration. Right? For those of you that did the pH titration curve last year, you remember that we didn't stop when the indicator changed. We kept going all the way until the pH stopped rising, right? So we can add an indicator to indicate to us the end point, but really we're going to be able to tell off of our curve when we reach the equivalence point. Okay, let me just slip two sides. Okay, so last year we did a lot of titration of sodium hydroxide and hydrochloric acid. The reason we often do that particular titration, in particular in Chem 20, is when we create our products, we make sodium chloride and we make water. So water, you know, is neutral, and sodium chloride, if you think about it, it's an ionic compound. It dissociates into sodium ions and chloride ions. Sodium ions are nothing. They're pretty much always a spectator. And chloride ions, if you look in your acid-base chart, I don't know if my periodic table here, well, it looks very different. It looks just a little different from what you have. But you'll see that the chloride ion, although it does appear in the conjugate base column, right, because there's two columns of your data table. Again, pretend I'm holding it this way so it matches up with yours, right? You have the acid and then you have the conjugate base. So what you're going to find is that although the chloride ion shows up in the conjugate base column, it's one of the first 6 acids. And remember, we said that the first 6 acids on our table are all strong, which means they go to completion. So technically those first 6 things that show up in the conjugate base column are not bases. They don't have the ability to be bases because we can't shift the reaction backwards, okay? So what that results in is us making sodium chloride, which is neutral, and water, which is neutral. This is why we find that our equivalence point is going to happen when the pH is 7. Okay, when we start titrating other things, so generally things that are not strong and strong, we're going to see that that's not going to be the case. And you're going to find that your equivalence point is going to happen at a pH that isn't going to be 7. Okay, now I think that slide just kind of explains it all, so just move to the next one. So this is the type of titration curve we talked about last year when we were in Chem 20, okay? So we get this classic sigmoid or S shape happening. We have our equivalence point happening at a pH of 7. Okay, that's what we expect when we titrate strong with strong. Okay, when you are looking at the curve, you'll notice there's this vertical section. The equivalence point always happens at the middle of the vertical section. So even when we start looking at other curves that maybe don't follow this perfect shape, you're still always going to be able to pick out the equivalence point because it's always going to happen in the middle of the vertical. Okay, so when I look at a curve, there's a couple of things that I need to be able to identify. I need to be able to identify whether I had a strong acid or a weak acid, and I need to be able to identify whether I had a strong or a weak base. There's a couple of things that are going to indicate that to me. One of the really common things is to look at your starting pH and your ending pH. Okay, oftentimes we're going to talk about cutoffs of 12 and 2. Okay, and oftentimes what you're going to find is that if your pH is greater than 12, which here it is, that's going to indicate to you that you are dealing with something that is strong. Okay, so we can say, even if I didn't know that this was sodium hydroxide, I could say that this was a strong base. And I could say that because the pH is starting greater than 12. Okay, and as we look at some of the other curves, there are some other things that we're going to look for as well that are going to indicate that to us as well. Okay, down here, when I look at my acid, I can see that the pH is ending less than 2. So because it's less than 2, I can also conclude that this is a strong acid. Okay, so we often talk about 12 and 2 as being some important pH numbers because they're going to give us an indication of strong or weak. Okay, some other things that we'll notice are equivalence points. So the middle of the vertical is always going to happen at 7 when we are titrating a strong and a strong. That's not going to be true when we start to change it up a little bit, okay? And we'll talk about that when we look at those curves. Okay, other things I need to be able to recognize is what started in my Erlenmeyer flask. So looking at this titration curve, we can see that on the x-axis it says volume of acid added. So that's already telling me that I'm adding acid, which means I must be starting with base in the flask. Okay, the other way I could have also decided it, if it just said like volume of titrant added, would be the fact that it starts with a basic pH. So starting with a basic pH obviously means we're starting with a base inside of our flask. We're going to see that over time as we add that acid, it is going to become more acidic. Okay, so you'll notice with the titration curves, we don't stop when we reach the equivalence point, right? So even if I would have had an indicator in here that told me to stop, I would continue going because I want to generate the whole curve. Because from a titration curve, my equivalence point is going to be a little bit more accurate than the accuracy with which that indicator is going to indicate to me to end my titration. So yeah. This is going to be running an acid into a base. We can also look at the flip of this, right? So this is the exact same titration. The only difference is what we started with in the flask. So in this titration, we started with the acid in the flask and we are adding the base. So notice for the most part, your curve just kind of flipped around from what it looked like before. Okay, still a strong acid because my pH began less than 2. Still a strong base because my pH ended greater than 12. Okay, you're going to notice they may not line up perfectly with the same pHs that we started with, and that's totally acceptable. We're still able to recognize that it's a strong with a strong. Okay, looking at our equivalence point, we find the vertical section, which is here. We find the middle, which is right here. That still corresponds to 7. Okay, so those are kind of my 3 pieces of evidence that tell me that it's a strong with a strong, and also that tells me that this is a monoprotic acid with a monoprotic base. Okay, so it's only one equivalence point. That's how I know it's monoprotic, and later on we're going to look at some that are polyprotic. You're going to see what I mean by there's only one equivalence point. I also can tell that it's a strong acid based off the starting point, a strong base based off the ending point, and that equivalence point of 7 does also confirm the fact that it was strong with strong, as well as this classic S shape. Okay, so now this curve looks quite different, right? We no longer have that classic like S shape going on. We also see our vertical is down here now. So when we find the middle of it, it's closer to, I'm going to guesstimate around 4.6, right? It's around 5. So you'll notice that it changed significantly. So if we look at what we actually titrated, we titrated ammonia with hydrochloric acid. So we talked about those numbers of 2 and 12, right? So if I look here, here's my 2. It's ending below that. That's indicating to me that this is going to be a strong acid. That makes sense. It's hydrochloric acid. Hydrochloric acid is one of the 6 strong acids. When I look at my base over here, 12 is here. You'll notice it starts below. Okay. The other really big indication is what I like to call this little dip here, right? If you flip back to the last curves that we looked at, it was more, excuse me, of a flat line or flat-ish line. When we look over here, we have this dip happening. So the dip, along with the pH less than 12, is indicating to me that this is going to be a weak base. Okay, you're going to find that on some curves, it's really hard to see the 2 and the 12, and that's because sometimes If you think about the diploma, it's multiple choice. They're going to give you 4 pictures. And so they're not going to be these huge blown up pictures. So sometimes it's actually easier to identify the dip than it is to see that 2 and 12. Okay, so if you see a dip, like you have in this one, it's automatically going to be weak. Okay, you're going to find that there are some acids in particular, those that are like just borderline, so they show up right below that grayed out one on your table. They sometimes will have pHs less than 2, and that's because if I make them concentrated enough, they can have that pH. But what I'll notice when I do the curve is they're always going to have that little dip. Okay, so look for a dip. If you have a dip, that's going to indicate to you that something is weak. Okay, so we have a weak base over here. We can see over here that we have a strong acid because it's ending below 2. You're going to notice that our equivalence point, so the middle of the vertical, is now less than 7, right? We talked about it being like 4.6, 4.7 in that range. So whenever I see that that happens, that's telling me that one of the products of the titration is acidic. And I know it's acidic because the pH is less than 7. So now the question becomes, what part is? So if we look at this, we produced ammonium chloride. So ammonium chloride is an ionic compound, right? When we think about ionic compounds, they dissociate when we put them into solution, right? So this is going to break apart to give me an ammonium ion as well as a chloride ion. So one of these must be acidic. So I can go to that acid-base table in the back of my booklet, right? We talked about how although the chloride ion is in the base column, it's not actually a base because it's one of the first 6 ones, right? So the first 6 bases at the top of the table are not bases. But ammonia, if you scroll all the way down in your table, somewhere on here, I don't know where it is on this one, way down here, so way down on the bottom of yours, it shows up as being in the acid column. So that means I've made a weak acid. Okay, this is why we find that the equivalence point is happening below 7, right? The chloride ion is neutral. It doesn't have any acidic or basic properties associated with it. But the ammonium ion is acidic, which is why we wind up with that equivalence point happening less than 7, okay? Trying to think if there's anything else I want to say about this curve. So I see a dip, I know something is weak. I see my equivalence point is no longer at 7. That's going to indicate to me as well that one of my things is weak. I should be able to recognize that one of my products is going to have acidic properties based off where the equivalence point is. You'll also notice, remember the other day we talked about conjugate pairs, right? You'll notice that ammonia and ammonium are conjugate pairs of each other. Okay, if you find them in your data table, ammonium is in the acid column and ammonia is in the base column. So generally what we're going to find is when we do something weak with something strong, we're always going to wind up with equivalence point properties matching up with the conjugate of whatever the weak species was. So because our weak species was ammonia, it was a base, its conjugate is going to be the opposite, right? Remember we said how like acids are paired with bases when we put them into conjugates and bases with acids. So because ammonia is a base, we're going to make its conjugate, which is a weak acid, which is that ammonium, which is why we wind up with that equivalence point not happening at 7, okay? All right, so here's that same titration curve, but flipped around. So this time we started with the acid in the flask instead of the base. Okay, so you'll notice the curve does look significantly different. It's not just a flipped image, okay? But I can still recognize strong and weak. Okay, you'll find down here, we're definitely starting well below 2. So it's still really easy for me to identify that this is strong. You're also going to find that our ending pH is going to be nowhere near 12, right? So the fact that there's no dip isn't really a problem because it's pretty obvious that it's below 12. And I also see that my equivalence point is not at 7. So I know something has to be weak. I know it's not the acid because the acid started at a super low pH. So it's going to have to be my base, okay? So this is what a strong acid and a weak base curve is going to look like. Between this one and the previous image, the only difference was we changed what we started with in the flask, okay? We were still titrating the exact same chemicals. Okay, so now we've changed it up again. So when I look at this, I see that my pH starts at 14. I'm well above 12. So I'm clearly dealing with a strong base. When I look over here, here's my 2. I'm way above that. So that must mean that we are using a weak acid and a strong base. Okay, again, my equivalence point is not at 7, right? 7 is down here. In this case, the middle of my vertical is happening just above 9. So that means one of the products of the titration is basic. Right? Remember in the last slide, we kind of talked about how if we had a weak base as part of our reaction, we were going to make its conjugate for a product. So here we had a weak acid with a strong base. So that means one of our products is going to be the conjugate of this weak acid, and it's going to be a weak base. That's why we see that our equivalence point is greater than 7. So when we look at what we titrated acetic acid or vinegar. This is a weak acid. We titrated it with sodium hydroxide, which is a strong base. So product-wise, we made water, which we know is neutral, but then we made this sodium acetate. Okay, so sodium ions are nothing. We don't ever care about sodium ions. They're pretty much always going to be spectators. I also know they're nothing because when I check that acid base table in my data booklet, they are not in there. Okay, if they're not in there, it's because they're not an acid or a base, okay? But what is in there is this CH3COO minus, right? So this part here, if you find it in your table, it's in the weak base column because it's the conjugate of acetic acid. So this guy here is what is giving us, well, that arrow went too far, but it's what is giving us those basic properties that we are seeing when we reach the equivalence point, okay? So I can recognize that it's a strong base based off the initial pH. I can recognize a weak acid based off the ending. I can also recognize that it was a strong and a weak titration because my equivalence point isn't happening at 7, okay? And again, at the end of the video, I'll show you some old diploma questions that kind of show you what kind of questions you're going to get asked about these, because a lot of times that's what you guys struggle with is, what am I going to be asked? It seems like there is so much that could potentially be asked. And although, yes, theoretically, there's a lot of stuff that can be asked, they're only going to ask you so much on a diploma because it is a multiple choice and a numeric response exam. All right, so here's that exact same titration that we just looked at. It's still the acetic acid with the sodium hydroxide. You're going to notice it looks a little bit different, right? My equivalence point is still the same, right? It didn't change. The middle of the vertical is still happening just above 9. It's still going to be a strong base. But when we look here, right, if you think about the other acids that we looked at, they had more of this like line that kind of went like this and came up. This has that weird little dip going on again, right? And so that's where I was talking about earlier about how when you have that dip at the start of the line, that's going to be an indication to you that you are dealing with something that is weak, okay? So that's telling me that this is a weak acid. It is also above 2, which is helpful, but like I said previously, the dip is more, or not more, but is a better indicator that you have a weak species than the 2 and the 12, because sometimes it's hard to see where the 2 and the 12 are, okay? So this is running a strong base into a weak acid. We know we started with the acid in the flask because of our initial pH, and we know that we were adding the base because we obviously saw that over time the pH of our solution was going to increase. All right, so now I got to look at a week and a week. So a week and a week looks kind of different, right? It doesn't really have any of that kind of S-like shape. It literally turns into this like rolling hill. And the reason for that is they're both weak. They're not going to have those extreme pHs that we talked about. So at the start here, I should be able to recognize that this is a weak base because we have our little dip. I should be able to recognize that it's a weak acid because the pH is way above 2. Okay, you're going to notice your equivalence point goes back to 7 or goes back somewhere close to 7. Okay, and the reason for that is when we titrate something weak with something else that's weak, we make products where one is a weak acid and one is a weak base, and they kind of neutralize each other out, which is why that pH goes back to being around 7, okay? The other big thing you'll notice with these ones is it becomes significantly harder to find your vertical section to identify the equivalence point, right? There isn't that like huge drop down like you saw in the other ones. You'll kind of notice there's the dip, it slowly drops, and then there's kind of a little bit more of a drop, and then it eventually flattens out. Which is why we usually say with these ones that we just throw the equivalence point in around 7, because it's really hard to identify where the middle of the vertical section is, because you don't actually have a vertical section to figure that out from, okay? So you should notice between the 4 different types, right? So strong and strong, a strong with a weak with a strong, and a weak with a weak. They have very different shapes to them, right? They look different. So you should be able to look at a curve and identify, was it too strong? Was it strong and weak? You should also be able to identify which of the things was the strong one and which of the things was the weak one. Right? So this kind of summarizes what those curves look like. Right? In this case, they all started with the base in the flask, right? You do have the flipped versions of starting with the acid in the flask, but they're all going to have the same general pattern, right? So a strong acid with a strong base, I'm going to have that classic S shape. We're going to have the middle of the vertical lining up with 7. Okay, here I can tell this is a weak base because I have the dip at the beginning. I can tell it's a strong acid because of where it ends. I can see that the middle of my vertical is going to be less than 7, right? So that's also an indication that something was strong and something was weak. Okay, here we have weak acid with a strong base. So we started nice and high because we had that strong base. We see that our equivalence point, or the middle of the vertical, is going to be well above 7. And then we see that our ending pH here is well above 2, which allows for me to identify that it's going to be that weak acid. Then we have the last combo, which is a weak with a weak. We get more of that rolling hill. The middle of the vertical goes back to 7. And we don't have any of that kind of classic S shape, right? At least with the other two, we have half of it, right? So like in this one, we have the upper half. And then in this one, we have the lower half. In this, we don't have any of that classic S shape, which is how I can recognize that it was a weak with a weak. So all of these curves are for monoprotic acids with monoprotic bases, right? So monoprotic means one hydrogen. So sodium hydroxide with hydrochloric acid, we're only transferring that one hydrogen. When we start looking at curves, like let's say we did sulfuric acid with sodium hydroxide, it's not going to look the same, right? Because sulfuric acid has 2 hydrogens. So if you think back to when we talked about ionization equations in Chem 20, we talked about how when you have more than one hydrogen, you're going to lose them in a stepwise fashion, right? And we wrote as many ionization equations as we had hydrogens. We're going to find that the same thing is true when we do titrations with polyprotic species. So if I were doing a titration with, let's say, sulfuric acid, it's not going to be that both H's just suddenly come off. It's going to work so that the first H comes off. Once the first H is taken off of all of them, then the second H gets to come off. So what we're going to find is when we have polyprotic species, depending on how many hydrogens we have, that's what's going to determine how many equivalence points we have. So in the case of sulfuric acid, because it has 2 hydrogens, we're going to have 2 equivalence points, which means when we look at our curve, we're not just going to have 1 vertical, we're going to have 2 vertical sections. So let's look at an example of that. So we're looking at sodium carbonate and hydrochloric acid, okay? So here's our balanced chemical equation. So Na2CO3 plus 2HCl to give us 2NaCl and CO2 and H2O. If we look at the curve, this is what it looks like. Okay, so you will notice when you look at this that we have 2 equivalence points, right? We have this little vertical section, and then we have this other vertical section happening here. So when we begin, you can see that we have the dip. So I know that I have a weak base. This makes sense because if we have sodium carbonate is going to dissociate because it's an ionic compound. So what that means we're really starting with is that CO3 2- ion. Okay, if you look in your data booklet, you're going to find that that carbonate ion is way down near the bottom of that conjugate base column. So it's a base. Okay, we're combining this with hydrochloric acid. So some of you might be saying, wait a second, why is this a polyprotic titration? Hydrochloric is only 1 H, it's monoprotic. But the thing you need to consider is bases can also be mono or poly. Okay, when we talked about bases as being mono or poly in Chem 20, we basically talked about how many hydroxides do they produce, 1 or 2. Okay, when we're in the context of Chem 30, it more so comes down to have a look at that charge. This has a 2 negative charge. If you think about hydrogen ions, they have a positive charge. So if this has 2 negatives, it can accept 2 hydrogens. That's why this is a polyprotic base. It has the ability to accept 2 protons because it has that 2 negative charge. That is why we have 2 equivalence points. At the first equivalence point, this is going to gain 1 proton. And we're going to find that at the point of this A, when we're at the equivalence point, what we have is HCO3 minus. So from this point right here to this point here, what is happening is we are taking a hydrogen from the hydrochloric acid and we are transferring it over to the carbonate ion. By the time we reach this point A, we no longer have any more carbonates. They have all been converted into the hydrogen carbonate ion. Okay, if I continue to add acid, which obviously I am, it's a titration, I'm going to keep adding. What's going to happen is this hydrogen carbonate is going to start to accept the second proton. So as I move from point A to point B, these molecules are gaining that additional proton. By the time I get to point B, which is my second equivalence point, they have all been converted into H2CO3. So I no longer have any more HCO3 minus, right? So it's important to recognize what species you have at different points in your curve, right? So here at the very beginning, the species I have is carbonate. As I move from the initial to point A, or that first equivalence point, I start to have a mix of carbonate and hydrogen carbonate, where the further I move along here, the less carbonates I have and the more hydrogen carbonates I have. By the time I reach point A, all I have is hydrogen carbonate. I don't have any of the other things. But as I continue to add HCl, I'm going to continue to add a hydrogen to this, and my HCO3s are going to start to convert into H2CO3s. Right? So as we move, we slowly start to convert them, and more of the HCO3 minuses turn into H2CO3 until I reach point B, where they're all converted into H2CO3. So I no longer have any carbonate because I lost that at point A, and I no longer have any hydrogen carbonate because I lost that at point B, or the second equivalence point, okay? So part of how we know this happens is we have different evidence that we see. So you'll see here it says no carbon dioxide given off at this stage of the titration. But then between A and B, we start to give off carbon dioxide. The reason this happens is as soon as we make H2CO3, this is going to start to decompose, and it's going to decompose into water and carbon dioxide. This is why we start to see that as we go along this point here, we're giving off carbon dioxide because we start to form the the carbonic acid. It then starts to decompose into the water and the carbon dioxide. We start to see those bubbles, okay? So it looks different because we have two equivalence points. We have two equivalence points because this has a 2 negative charge and it has the ability to accept 2 protons, okay? I know it's weak because it started less than 12 and it also had that little dip happening. And then over here, we know we added HCl because the question told us that, the example told us that, but I also can tell that it's strong because it's ending below that pH number of 2, okay? So, important to be able to recognize how monoprotic and a polyprotic titration differ. Monoprotic titration only had the 1 equivalence point. Polyprotic titration is going to have as many equivalence points as either your acid has H's or your basis has negatives, okay? You're going to find that in the polyprotic titrations, one of the species is always going to be monoprotic. So in this case, we had HCl that was monoprotic. Then we had the sodium carbonate, and that was our polyprotic one. We're never going to be like, oh, it's sulfuric acid and sodium carbonate. We're not going to do that. It will only be one of the two being polyprotic, okay? And then you can figure out how many equivalence points you should have based off of either how many H's does it have if it's the acid that's polyprotic, or how many negatives does it have if it's your base that's going to be polyprotic. Okay, so that just kind of talks about what we broke down. If you want to read that, you definitely can if you missed a piece. So next titration. This time we are going to use, they're calling it ethane dioic acid, but we often call this oxalic acid, okay? So we're titrating oxalic acid with sodium hydroxide. So we look at that. Sodium hydroxide is a strong monoprotic base, right? I know it's strong because it's a group 1 hydroxide. Remember, group 1 and group 2 hydroxides, with the exception of beryllium, are strong bases, okay? It's monoprotic because it only has the 1 OH. But then we look at oxalic acid. So if you look in your acid-base table, oxalic acid is a weak one. But it's not that weak. And what I mean by it's not that weak is it's just below the cutoff for strong and weak, right? There's that grayed out one that kind of is the breaking point of strong above it and weak below it. And I want to say on your table, it's the very first one below it. So it's a weak acid, but as far as weak acids go, it's a stronger weak acid, okay? So why I'm saying all of that is when you look at this curve, sometimes you guys are like, no, this is strong. Look at that pH, it's starting below 1. And so this is where you have to remember that there's 2 ways to manipulate pH. One has to do with the strength, right? Is it strong or is it weak? But the other one has to do with the concentration, right? If I have a really concentrated acid, even if it's weak, I can manipulate that pH to be less than 2. And that's why I was saying the dip really is going to be your best tell for the fact that it is a weak one, okay? However, because it's a stronger weak one, we definitely have a little bit more of that classic S shapes happening. So really easy to identify that we have 2 vertical sections. So that means that we have 2 equivalence points. That makes sense because when you look at the formula for the oxalic acid, it has an H on this end and an H on this end. So it's diprotic, and I say diprotic because it has 2 of those protons. So when we start our titration right here, we're starting with that HOOCCOOH, right? We're starting with just oxalic acid in our flask. As we begin to add base, though, we start to remove one of the protons, right? Because it happens in a stepwise fashion. So when we get here to the middle of the vertical section, all of this is converted into this, where we've taken away that very first hydrogen. We don't have it anymore. So now we have OOCCOOH minus, right? We also are going to have, what is it, sodium ions, because we also titrated this with sodium hydroxide. And obviously we're going to have water. But yeah, so that's what's going to happen here. Then as we continue to add base, we're then going to start to remove the second hydrogen ion. So as we're moving from this point to this point, we're now taking the second one off. By the time we reach the second equivalence point, we have now completely removed the second hydrogen. And we are left with that OOCCOO2 minus ion, okay? So different points of my curve, I have different species happening. Okay, this is important to be able to recognize for when we get into our titration calculations for these. It's also going to be important to recognize when we start talking about buffers in a few days, because we're going to come back to these titration curves and talk about what buffers are and how they work, okay? So you should be able to recognize the difference between mono and poly because of those additional equivalence points. So let's have a look at a sample calculation of what these are going to look like. So what is different about these than the titration calculations you did last year is when we are dealing with multiple endpoints, like we did in the last two, right? Both of those had 2 endpoints. We're going to find that the titration data we have collected is going to be for one of the 2. So when I go to write my balanced equation, that's the part that's really going to be different. And the reason it's going to be different is I need to know, what am I writing an equation for? Am I writing an equation for the first equivalence point, where the HOOCCOOH minus has turned into OOCCOOH minus, or am I writing one for the second equivalence point, where the HOOCCOOH has turned into the OOCCOO2 minus? Okay, so really important to make sure you read the question carefully, because what's going to happen is if you just assume it's the final endpoint, which tends to be what you guys do, because when you guys are used to writing these titration calculations, you just want to do double replacement because that's what you've always done. And if it's the final equivalence point, you can do that. But if it's not the final equivalence point, then you've written the wrong equation. And what's going to happen is your ratio is going to be incorrect. And that's obviously going to result in the answer to your calculation being incorrect because you use the wrong ratio. Okay, so the hard part of these is not the stoic calculation, because the stoic calculation is the same as what you've always done. The part you need to practice is writing the equation, because it's not necessarily going to be double replacement. It's going to be really important for you to read the question and make sure that when you create your products, you're actually creating the right species. So looking at this example, it says several 15 ml samples of oxalic acid were titrated with a standardized 1.50 mole per liter sodium hydroxide solution. This pH curve has 2 endpoints. The following information was collected following the first quantitative reaction. Okay, and that is important because that's telling me that we are collecting data for the first equivalence point. Okay, then it's asking me, what is the concentration of the oxalic acid solution? So generally what I suggest you guys do with questions like this is kind of write out your polyprotic. So start with that one, right? So I would be like, okay, out of the 2, sodium hydroxide is monoprotic, but the oxalic acid is polyprotic. So we have our HCCOOH, right? So that's my starting point. If we go to the first equivalence point, we get to take 1 H off, right? And we have OOCCOOH minus. If we're going to the second equivalence point, then we get to take both H's off and we produce the OOCCOO2 minus. Okay, why this is helpful to do is so that you can go back to the question and figure out which one of these is actually my product. right? This is obviously going to be my reactant. It's what I'm starting with. But product-wise, I need to make sure that I'm creating the right one. So because it told me it was the first quantitative reaction, this is the first one, right? Because first, second. So product-wise, I need to be using OOCCOOH minus when I am writing my balanced chemical equation. So we start normally. We start with our oxalic acid. Okay, we are going to combine that with the sodium hydroxide. So product-wise, this is where this is different. Okay, I'm not just going to do double replacement because this isn't going to the final endpoint. So what I want to recognize when I am writing this is the equivalence point I'm going to and what I'm making. So we already established we're going to the first equivalence point. So my product is going to involve the OOCCOOH minus. And it's going to do that because what we're going to do is take this H off. We're only taking one H off because it's the first equivalence point. Okay, this H, because we combined with sodium hydroxide, is going to get paired with this OH. So we are going to make water. Okay, our other product, we still have this OOCCOOH minus. We also have this sodium ion, which hasn't been paired with anything. Sodium has a positive charge. This ion here has a negative charge, so they are going to go together. We're going to have NaOOCCOOH. And that is going to be aqueous. Okay, so first equivalence point, we need to make sure we identify what species we have at the first equivalence point, and that we actually have that in our products, okay? As a general trend, you are going to find that if it's the first equivalence point, your equation should all balance with ones. If it's the second equivalence point, you're going to find you have some twos. If it's the third equivalence point, you're going to find you have some threes, okay? So the next example is going to, I think, have that in it for us. So once I write the balanced chemical equation, this is literally just a regular stoic question. So I have three experimental pieces of information. This one here says dark pink, and light pink. I am going to eliminate this trial because it's the one that isn't like the others. So that leaves me with these two trials that I am going to be working with. So it gave me a final burette and an initial burette. So to figure out the volume that we actually used, we get the difference. So it's 26.2 minus 13.4. That tells me we used 12.8 milliliters here. And I know it's milliliters because these were both given to me in terms of milliliters. Okay, then over here, we had 39.3 minus 26.2. So we have 13.1. Apparently I deleted the color, didn't need to do that. It should say light pink. Okay, so we're going to average these two trials. So we're going to do 12.8 plus 13.1. We're going to divide by 2. So we know that the average volume is going to equal 12.95 milliliters, okay? So now that we have that, we should have all the info we need. So it was 15 mil samples of oxalic acid. So we know this was 0.0150 liters. We know the volume of sodium hydroxide because it's the average, so 0.01295 liters. And then we are given the concentration of sodium hydroxide as 1.50 moles per liter. Okay, and what we were trying to find was the concentration of the oxalic acid. Okay, so at this point, it just becomes a normal stoic question. So you can go ahead, do your unit analysis. So ratio 1 mole of our oxalic acid over 1 mole of sodium hydroxide. Okay, we need to get rid of moles of sodium hydroxide, so we are going to times by the concentration of the sodium hydroxide, so 1.50 moles NaOH, and that is going to be per liter. Okay, that now lets us cancel out moles of NaOH. Okay, we need to get rid of liters of NaOH, so we are going to times by that 0.01295 liters. We now got rid of liters of NaOH. Last thing we need to do is introduce liters of the oxalic acid. So we're going to times by 1 over 0.0150 liters. So some common mistakes you guys tend to make usually has to do with this average volume when you go to plug it into your calculation. Sometimes you guys like to round this. Don't round it, because if you round this number, that's going to impact your final answer. So make sure that you do use that whole number once you average it inside of your calculation. So now what are we going to get? We are going to get the concentration is 1.30 because we can have 3 significant digits, moles per liter. Okay. Okay, so here's another example. So we have a 25 ml solution of phosphoric acid is titrated with a 1 mole per liter solution of potassium hydroxide. At the second endpoint, the volume of potassium hydroxide used was 18.5 mils. What is the concentration of phosphoric acid? So we want to recognize that it's telling us the second endpoint. Okay, so we're dealing with phosphoric acid and potassium hydroxide. So our polyprotic species is the phosphoric acid, right? And phosphoric acid to start with is H3, what am I typing? PO4, right? And then that's going to turn into an H2PO4 minus, and that's going to turn into an HPO4 2 minus, right? We're just continually removing that one proton, and then finally it turns into PO4 3 minus, right? So what we're starting with, there's the first equivalence point, there's the second equivalence point, there's the third equivalence point. So this question specifically talked about the second. So if this is what we started with, this is the first, this is the second. So we need to have HPO4 2 minus as one of our products. So reactant-wise, we have phosphoric acid, so H3PO4, aqueous. We are combining that with potassium hydroxide, which is also aqueous. So I'm just going to make that a little bigger. It's small. Okay, so that is going to turn into, so what is it going to turn into? We know that we're going to make HPO4 2 minus, okay, because it's going to the second equivalence point. It has 2 negatives. Because it has 2 negatives, we need to partner it up with 2 positively charged items. The only other positively charged thing we have is the potassium. Each potassium is a +1 charge, so we're going to need 2 of those to partner up with this. So we are going to be making K2HPO4. Okay, so there's the HPO4 part that we knew we had to have because it was the second equivalence point, and 2 Ks because HPO4 2 minus has a 2 minus charge, so it needs 2 Ks. Okay, other product, if you think about what we removed, can I type properly? Apparently I can't type. There we go. Okay, so what did we take away? We took some hydrogens away. We took some Ks away, right? The K swap spot with the hydrogen. So that means these H's are going to go with the OH's, which makes sense because most of the time when we do a titration, one of our products is generally going to be water. So this equation isn't balanced. And I know it isn't balanced because I have 2 K's over here, but I only have 1 over here. So we're going to fix that by putting 2 KOH in. Okay, remember earlier I talked about how depending on the equivalence point, you're going to find that the coefficient that you use is going to match that. So when you're at the first equivalence point, it should balance with 1s. If you're at the second equivalence point, your monoprotic species should get a 2. If it's the third equivalence point, your monoprotic species, I'm having trouble talking, should have a 3. So other thing that's going to need a number is going to be the water, right? This also needs a 2 so that my equation is balanced. So now that my equation is balanced, it's just a matter of doing some stoic. I'm going to stop here because it's 50 minutes and I think you guys know how to do some stoic. But yeah, so this is what your multiple endpoint titration calculations are going to look like. Really important that you practice them, and in particular, practice the writing of the chemical equation. If you took Chem 22nd semester, probably also a good idea to make sure that you are also practicing that stoic, to make sure that you are comfortable with doing it, because you will get stoic questions on the diploma. You have to be able to calculate them. But like I said, really the hardest part of this is going to be to write those balanced chemical equations, because they're not just going to be double replacement, and they take practice to figure out what equivalence point am I going to, what's the product going to be, and then how do I actually make that. Okay, so that's kind of your titration curves and your calculations for when you have those multiple endpoints.